Welcome. In today's tutorial, we are going to finally jump into what's called supervised data mining, in which going beyond unsupervised data mining, in which we try to establish patterns, what goes with what, clusters, etc. Now, in supervised data mining, we have something that we're interested in predicting or classifying, be it sales or whether or not a customer will default or not, and that we call our label. So sort of the analog to the dependent variable in statistics. So to begin with, today we're going to run a linear regression as our first method of supervised prediction. And we are also going to talk about how we can prevent any possible overfitting from occurring, and how do we validate our model in the data mining framework or philosophy. So to begin with, let's have a brief look at the data set that we're going to be working with. And as we see, we have 768 observations. In this case, it's about buildings. Specifically, we have different units here. So we have our ID variable. We have our label. So RapidMiner designates this in green. So this is what we're interested in actually predicting, which happens to be the heating load of houses. And we have a whole bunch of attributes of explanatory variables that we may leverage when it comes to try and predict heating load. So we have data on the relative compactness, surface area, wall area, roof area, overall height, orientation, glazing area, and glazing area distribution. I'm sorry. Okay. So we could go into some more data exploration and visualization, but for now, we're just going to focus on how we would run the linear regression in RapidMiner. And so to begin with, as you might intuitively have presumed, all we can try to do is to get a linear regression operator connected. So now our data set goes into the linear regression. And what comes out of this linear regression operator is a model, the example set, and we're not going to be concerned much with these weights. And essentially, what we could do is we could run the model, estimate the model, estimate the coefficients in this case, and our intercept, and then we could apply this model basically to our data set. Okay, so we've got some data, we're going to estimate a linear regression on that data set, we're going to apply that same model on the same data set, meaning that we're going to get predictions, in this case for heating load. Okay, and then we can look at the performance of our prediction. And in this case, we're going to want to use the regression performance operator, which is for numerical labels or dependent variables. And so what it wants is, again, it wants the labeled data. This is after the model has been applied to in this case, our initial example set. And what we're going to get is, again, we're going to get that same data, but most importantly, we also are going to get a performance vector, okay? And what this includes is basically up to us to choose. So we haven't gone into any of these settings of the different operators yet. But let's take a moment here and see what would happen. So we've got our data set. We're going to estimate this equation of our linear regression. We're going to apply this to our data set in order to create predictions for our observations, and we can measure performance. A couple of things we would do, just to keep it simple for now. So if we go into linear regression, we would deselect in case you were hiding your advanced parameters. For linear features, feature selection, none. This basically talks about whether or not we want to select a subset of the variables that we feed to the regression. So for now, we don't want to do that. We just want to use all of the different attributes. In the apply model operator, we don't have to do anything. In performance, here's where it gets interesting. Basically, we can ask for the RMSE, which is the root mean squared error, which gives us a good idea of how good of a fit our model represents or creates with respect to the actual true observations. We'll look at that in a second. What you're going to be more familiar with, based on what we've previously done, is of course the squared correlation, which will give us the R square. And we can ask for a couple of other things, but for now, let's leave it at asking for the R square, which again gives us a good idea of how much of the variance in our data are we explaining through our model. And we'll use the RMSE as a different way to look at how well do we fit our prediction, how well do our predictions fit to the actual data. Okay, so we'll just select those two, and just to see what would happen, let's run this. And the only thing we'll look at for now is basically this labeled data set that we're getting based on having run the regression. So we're getting our performance vector, and we're getting also our data set. This is basically the two things that come out of our last operator here. And so what does this give us? Well, it gives us basically our label and the actual true observations with respect to heating load. And then based on our regression model and the use of all of these different attributes, we've created predictions for heating load. Now, as you can see, they don't always actually correspond to the true values. As a matter of fact, they rarely do. But we're not interested in exact matches. We're interested in how well they are, more or less on average. And that is something RMSE gives us. So at the end of the day, we're interested, whatever performance measure we look at, mainly in minimizing the distance between our predictions and the actual true observation. So we want to have a model that fits as best as possible. Now, something we actually haven't asked for here is our regression model, so we could get that and connect that as well. And this would now also give us the type of sort of familiar coefficient values, as well as the intercept, as well as some further tests on those coefficients if we were interested in testing for whether they were actually truly different from zero, statistically speaking. But the real upside of a linear regression as a predictive method is that we're getting coefficients that we can interpret. So we can try and explain why, in this case, a certain heating load results, provided that the house has a certain wall area, roof area, overall height, etc., etc. Okay, but without spending a lot more time on this, let's go back to our design tab, and let's think about what we've just done. Basically, what we just did is we got some data and we ran a linear regression, and we looked at we haven't really looked at some of the performance measures, but we could look at R square, and we could look at the RMSE, and we could say, well, this is sort of how it performs. But there's a big problem here, And that is that we are essentially using the same data to estimate our regression, and we're also applying our regression to the same data with which we've estimated the regression, and then we're measuring our performance. In this case, we've just run a very simple regression without using any feature selection or anything else. But later on, instead of using this linear regression in order to predict heating load, we may also use other algorithms and approaches to predict heating load. Equally for this linear regression, we could now go into feature selection. We could create a couple of new variables to look at nonlinear trends, etc., etc. And what would happen is that we would increase the complexity of our model, and we would run into an overfitting problem, basically. And so estimating our model on the same data for which we then later test its performance is a bit of a deceiving way to test the validity of your model, because you are probably beginning to model some sort of random error by increasing the complexity of the model. The performance will keep increasing, but it will be deceiving in the sense that if you were ever to use that same model specification for new data, it would probably perform very poorly. And this is where the whole philosophy of a test set as well as a training set comes in, and allows us to prevent this overfitting problem. And what's the idea of a test as well as a training set? The idea of a test and a training set is that beginning with the training set, we would like to take only part of our data here and estimate a linear regression on that training set, so to speak, to train, in this case, to estimate the coefficients of our model. And then we would set aside that training set and look at the test set, which was the other part of our data that we set aside at the beginning, and then apply that regression model, in this case, that we've estimated in our training set on the test set, look at the performance there, look at how it does, simulating in simple terms the performance of the model in new data, right? And that's basically the idea. So if we were to increasingly overfit in our training set, then at some point, so we're getting a better and better model, which would also show up in the performance measure in the test set, but at some point we would suffer, and we would basically see decreasing performance in that test set. Okay. Now, this being the idea, it turns out that we can get a little bit more fancy, and we'll talk about all of this in much more detail in class. But instead of just splitting our sample, which we could do with the sample operators or others, into two parts, one to use for estimating, in this case, our regression, and then the other part for testing the performance of the regression, we're going to work with something called cross-validation. Cross-validation basically performs this idea of training and later testing, but instead of simply splitting our data set here initially into two different subsets, cross-validation performs this idea of training and later testing various times. In this case, and we're going to keep that at 10 times, and also it's doing it 10 times because it's basically splitting that initial data set into 10 different subsets and then interchanging one of the 10 to train the model and then the other 9 of the 10 to actually test the model. So we're going to talk about this in more detail in class, but that's the idea of cross-validation. It's basically a very conservative way of training and then later testing to get a good idea of what's the actual real performance of the model in new data or for new data. Okay, so let's look at what this operator needs. As you can see, because it's sort of cascading windows, there's something inside of this operator. And if we double click on it, we go inside, and as we see here, this is exactly what we expect. We have a section called training and a section called testing. And what it wants in the training section is basically it wants some sort of algorithm or model to be unleashed on that training data. And what we get is a model. Okay, so here we would estimate a model on the training data, and then we would test that model on the remaining 9, in this case, 9 of the 10 subsets that were set aside, that were not used for training. Now they're going to be used for testing, and we're going to basically record the performance of this test. Okay. Now, all we need to do in order to run the linear regression using cross-validation is basically just copy-paste now our operators that already exist here. The first thing I'm going to do, I'm going to cut this linear regression operator, and that's what we'll want to use here for our training set. Okay, let me collect this. Let me actually connect this here first. So all I'm doing is I'm feeding the data into our cross-validation operator. Okay, and then if we go in, the training data gets connected to the linear regression operator. And what goes out is the regression model in this case. Okay. And as before, we're running a simple linear regression, not doing any feature selection or anything else. What's missing, of course, is applying this model that we are going to train in the training, with the training subset, and test this, basically apply this model and measure and record the performance in the testing set. And in order to do this, all we need to do is go back and cut out our 2 operators which apply the model and then measure the performance and paste them here. What do we need? The apply model operator wants the model, and it wants the data to which the model is supposed to be applied to. So what we get here as an entry for testing is our test data set, and we're going to feed this to the apply model operator. And then what we get basically from the apply model operator is our data, which now includes the predictions. So what we're doing specifically is we're using the model, the linear regression model that we've created in our training set, and then we are using, we're applying that model to our test set in order to create predictions for the test set. So using the same coefficients, but now with new observations, creating predictions, creating heating load predictions in this case, and then we're measuring those predictions against the actual true heating load, and we'll get our performance measure. And then we, of course, want to save our performance measure. And what we can also do is we can save basically the test set with those predictions, but we don't necessarily need that. What we're interested in is really the performance data for now, okay? And so we could also ask for our model, of course, but we will do this outside here. So we've specified basically our cross-validation operator. What we can ask for is we'll ask for our model, and we'll ask for our performance, of course. And what we can ask for, as we were just saying, we can ask for the predictions at the end for the test set. We can ask for, we wouldn't really ask for the example set, we would ask for the predictions for the test set. So we can connect that. And so this should take a little bit longer to run now, but what it's going to do is basically run 10 regressions on using different training and test sets, and it's going to make sure that we don't suffer from this overfitting problem. So let's run it and see what happens. So what we're getting, again, we're getting here our example set. We're getting basically our regression coefficient and all these stats from the regression analysis. And we're getting our performance vector. And in our performance vector, what we're getting is the RMSE, which we want to minimize. And it's kind of hard to compare to anything else at this point because we don't have rivals or other models or other specifications. And we also get our R square here, which happens to be incredibly high. Okay, so this is what we get. We can now use these coefficients to interpret the model, but what we've done is we've made sure that we don't simply estimate the regression and then try to validate that regression on the same data set. So we've used a training set to train the model, and we've used a test set to validate or to basically test the model. Something that we could do, so let's have another look back here in the results tab in terms of the RMSE. So it's a 2.933. And something we could do is we could go into our linear regression operator, and the only thing that we're going to play around here with is we can do some sort of feature selection, meaning that it's going to try out different combinations of the variables, the attributes, in order to have a better model. And what we can use is M5 prime. M5 prime is sort of the analog of maximizing the adjusted R square. Okay, that's something else that should be still familiar to you. And if we select this, it's going to do some automatic variable selection for us. And let's see what happens. Let's just run this as that. And we're getting the same stuff. Has anything changed? It seems that we're using less variables. So we now have 3, 4, 5, 1, 2, 3, 4, 5, 6, 7 variables. I believe overall we have 8 variables. Yeah, 1, 2, 3, 4, 5, 6, 7, 8. So one of them is no longer used. Okay. And let's go back to the results here. Something else that may have changed, hopefully, is performance. And, well, maybe it's gotten just a little bit better, not by much, it seems. But so at this point, obviously, our task would consist of trying to see how can we get a better fitting model. And once we're done, if we're happy with it, we can look and work with the predictions that we've generated and all sorts of other beautiful things that we'll do in the future, such as predicting for new data for which we may not necessarily have the actual label. We can use other ways of doing feature selection to optimize our performance. And of course, instead of using linear regression, we can use a whole bunch of other approaches. And we will generally do this using cross-validation. And that's basically the idea. And that's it for today.